we'll study the limits of efficient algorithms. Okay, so far we've been trying to come up with more and more efficient algorithms, and today the question is, are there limits to how well we can do? Okay, so that's the general question we want to start with. Okay, so firstly, a couple of announcements. Hopefully all of you have seen both of these before. So homework 3 is out, it's due. Also, I've posted solutions to homework 1. Homework 2, I think the last day for submission, I mean with any kind of points, will be this Sunday, so I will post stuff, the solutions after this Sunday. So, I mean, people can still do late submission. Hopefully they won't do it, but yes. Okay, so this is what we want. So here maybe you want to take a look at this reduction problem, the one about, I think it was question 3. If things are not monotone, what happens? So many of you had trouble, I think, articulating that problem. So maybe you want to take a look at the solution, or whatever else you want to do. Okay, so this is a question for the day. Okay, so are there limits to how efficiently we can solve problems? Okay, so one question you can ask is, let's take some very extremely trivial problem. Okay, so let's take some problems like sorting, and you can ask yourself, okay, so if you have n numbers, how quickly can you sort them? Right? So that's the one we know, right? So we all know n log n. But can we do better? Can we do n?
Are we doing a comparison?
Sorry?
Are we using comparisons or?
Yes, that's the question, right? So we'll get to that.
We can do n if you're grading stuff.
Yeah, so yeah.
So if I know the limit of n, I can do rocket sort.
Yeah, so we'll get to that. So we are jumping ahead. So this is a very simple question you can ask, and more generally you can ask, okay, so you have various natural problems, right? Like we saw spanning trees, we saw various algorithms, we saw all pair shortest paths and so forth. And you can ask yourself, okay, so can you actually say that you cannot solve them quickly? Okay, so we saw, for instance, for all pair shortest paths, some algorithm that takes something like n to the 2 point something. Okay, so we haven't really seen it, but we can kind of do it. Okay, so if you guys think for a bit, you will be able to come up with it. But the question is, can you do it faster than this? Okay, so for any problem, we can ask this question, right? So is this the best we can do? Okay, and we want to get a sense of, okay, so how do we answer questions like this? So that's what we want to get at. Okay, and we'll start with a very simple example of sorting and take cues from what people have been saying. Okay, so we know that you can sort in time of n log n, and the question is, maybe you can ask, okay, can you do O of n? And so it turns out that, so this is precisely what he was saying, that if you restrict your computation model, okay, so if I tell you that the only way you have access to the array is by comparisons. Yeah, and what do I mean by that? I just mean that I'm given some array A that I want to sort. Okay. Now I can only ask you, is A of I less than A of j? So this is a very weird model, right? But because, you know, in some sense, you're not even allowed to ask what A of I is. So this, but it turns out most sorting algorithms, this is all you need. Okay, so like merge sort and almost anything you want. So you don't literally need access to what the entries are. You just need to be able to compare any two given entries. And of course, the comparison operator should satisfy triangle inequality and so on. Okay, so if I have I less than j, j less than k, I should be less than k. Okay. So this is how most sorting algorithms operate. And what you can show is that if you have an algorithm that only works by comparisons, then it has to take at least n log n time. Okay, so in fact, you can prove that it takes at least n log n comparisons. Okay, so notice what we've done, right? So we have we started off with this question: can we do sorting in O of n? We don't know the answer to this, and all we are saying is that if I restrict the model, if we restrict, what can be done? Restrict the model of computation. Then n log n is best possible. So this is one way in which you can answer questions like, is this the best possible algorithm? Okay, so you can say, oh, all the algorithms I know of happen to work like this. So can I restrict, can I say that no algorithm of this kind can do better than what I'm doing? Okay, so that's one way you can say stuff. Okay, so let's see how you can prove this. But actually before that, so how can you sort without comparing? Okay, so this is what he was getting at, is that sometimes you might know something more about the numbers. So suppose I told you all the numbers lie between 1 and 100n. So how do you now sort these numbers in time which is better than n log n? Think of n as being extremely huge. So can you do it in just time O of n? Yeah?
We could use auxiliary space, large auxiliary space, an array of let's say 1 to 100n. And every time we traverse the array, and every time we encounter an element, let's say 5, so we increment the counter in 5, and then we just read off this entire auxiliary array.
Okay, so does that make sense? I don't know if everybody could hear it, but he said it very clearly, right? So you're saying that you just keep a count of the number of times an integer appears, and you keep a count for all numbers from 1 through 100n. Okay, and for each number you have a count. And then you go from left to right and just keep outputting that number count of 5 times. Okay. And that should give you the sorted array. Okay, so that's this is one way to do it, and this takes time only over. But in some sense now you have additional information, and now note that you are not comparing anything. Okay, so you actually have literal entry-wise access to the array. Okay, so this is one way you can beat, for instance, this the n log n problem. And this is also, I mean, you can think of radix sort as doing something similar along these lines. Alright, so why is it, let's see a proof of this result though. So why is it that when you only allow comparisons, you need something like n log n steps? Okay, so let's see why that is true. Okay, and part of the point is to tell you how to reason about things like this. Okay, so if you remember, in the very first lecture, we talked a little bit about I think binary search, and the question there was, can you do binary search better than log n? Okay, so I think somebody asked this question, and I said that when we come here, so after this lecture, you should be able to go back and prove to yourself why does binary search need something like log n steps. Okay, so there were I think some nice questions about what if we partition the array into 3 parts and things like this. Okay, so I don't know if you guys remember. All right, so let's try to prove this. And the main question you've got to ask yourself is, so suppose I have some algorithm that sorts only by comparing elements. Question is, how can some such algorithm look like? Okay, so what do I mean by that? So suppose you have an array of size n. Okay, so I've got this array a1, a2 up to an. Okay. Now, any deterministic algorithm that takes something like n log n steps, or takes whatever number of steps, but it only does comparisons. the way it should look is, first it should ask me some question, right? So it should ask me, okay, compare A2 with something else. And it always asks only pairwise comparison. Okay. So it must ask you, keep asking you a sequence of questions. Okay. So any algorithm like this, okay, so any comparison based algorithm. So it must first ask you some two elements to compare, then it can do some calculations. Okay, so it can go off, do some computations, then it figures out some next question to ask you, and so on. Okay, and the questions it asks will depend on the questions it has asked before. Okay, on the answers to the questions it has asked. Okay. So is it clear how? I mean, intuitively, this is what any algorithm based on comparisons would do. Right? So it asks one comparison, thinks for a bit, asks another comparison, and so on. Okay, it can do some manipulations, have data structures, but we don't care. Okay. So I'm going to abstract any algorithm as follows. So I'm going to write down the first comparison it asks as a node in the tree, where I say it asks, okay, is AI J1? Okay. And you give it some answer, right? So you might say yes, you might say no. If you said yes, it can go ahead and ask some other question. Okay, so it can say, I mean, it could have done a lot in this process, okay, but we don't care at this point. Okay, so we only care about what comparisons it's asking. Okay, so then it can ask you, is AI2 less than AJ2? And here it could ask, is AI2 prime less than AJ2 prime? And so on. So any comparison based algorithm, you can think of it as this tree, right? Because you're just saying the algorithm starts off with one question. Based on your answer, it either goes to the left subtree or the right subtree. Okay. So you can think of any algorithm this way. And you have a tree like this. And in the end, you have some final comparison. After that, it's supposed to give you the sorted list. Okay, so is the modeling clear? So this is how we want to think of any algorithm. Okay, and in the middle, it could have done lots of steps, but we don't care. So that's what this is. All right. So now, what is the number of comparisons that an algorithm does? Also, by the way, this need not have a uniform depth, right? So for sometimes after a certain number of comparisons, it could say, oh, okay, this is the sorted list. Okay? Sometimes it might ask you further more questions. Okay? So somehow the depth of this tree is not always the same. I mean, this subtree could have a different depth than this subtree. Yeah?
Can you explain that prime, AI prime, the rotation?
Oh yeah, so that's just, I was saying that if I answered yes to the first question, the next query could have been some, is AI2 less than AJ2? But if instead I had answered no, it could have chosen to ask a different question.
I mean, are those different elements from the same array?
Oh, right, so actually, yeah, so these are all the numbers, right? So these are A1, A2 up to AN are what I call the array. I mean, if you want, I could write it as A of 1, A of 2, and so on. If I mean the same thing. Okay, and I1, J1 are just some indices. Yeah, so I1, J1, I2 prime, I2, J2, I2 prime, J2 prime. These are all some indices. Yeah, because
Yeah. Just some numbers.
yeah, there is some number between 1 and n. Okay, so it's yeah. Yeah, I just want to be general enough, so I'm just writing that. Okay, so all right. So is this tree clear? And so note that any deterministic algorithm, there is a unique tree like this. If you have a randomized algorithm, you could have different stuff. Maybe the I1, J1 is probabilistic, so on. Okay, but we are not considering randomized algorithms for now. Yeah.
So in this, are we assured that once the comparison is done, the algorithm remembers that and it does not make the same, or is it in the same path it does not make, but in a different path it could choose to make the same kind of comparison?
So the algorithm can do what it wants, right? If it wants to, it can do the same comparison it has done before. But the point is, it doesn't matter, right? So in some sense, it's only wasting memory. I mean, it's only wasting comparisons if it chooses to do that, right? So it's allowed to do anything. But all you've got to remember is that any deterministic algorithm, you can write down this tree. Yeah.
So the elements in the array might change for a particular algorithm. So it might need to have make the same comparison again.
Oh yeah, so that's the other thing. So maybe I should be clear on this. So we are thinking of, so this is the other standard assumption that we make, which is that we are thinking of the A as being fixed, and if it wants, you can, I mean, if you really want, you can think of the algorithm first makes a copy of A and calls it B or something, and that it's allowed to change freely. Okay, that takes only n time, right? So that it's allowed to change however it wants. But at every step, I mean, yeah, you're just allowed to compare. So the A itself you think of as being fixed.
So all comparisons are made on A, not on B.
I mean, so what do you mean by it's allowed to change A, right? So suppose it swaps A elements or something like this, right? So if it swaps things, you can assume it swapped actually the elements of B, but A is still whatever A was.
But the next comparison will be made on A again.
Right, so but corresponding to any element of B, there was an actual element of A, right? Which, and you can assume that those are the ones being compared. Okay. So, yeah. Because anytime you compare, you only compare two original elements of A. But that's a good question, okay? So, anything else? Alright, so this is what it is. And now, what is the number of comparisons this algorithm makes? If I gave you this tree and I told you what is the maximum number of comparisons this algorithm could make?
The maximum depth of the tree.
The maximum number of nodes that it can have.
Yeah, so it's the number of nodes, you said? Well, it has plenty of nodes, right? It has nodes at every
The maximum
thing. I mean, it's not, so at the end of the day, I just have one array. Okay? So, and the execution is essentially a path in this tree from root to the leaf. Okay? So in some sense, that is the number of comparisons, the number of nodes on this path, which is basically the depth of this tree. So number of comparisons in the worst case is equal to the depth of the tree. And depth as usual is defined as the maximum root to leaf path length. So it's there could be one leaf out here, but that won't be the depth. So the depth is by definition the largest length along. Yeah.
It's not clear why the comparisons would be only a traced path and not all the nodes, because in the structure all the nodes there is a comparison associated with it.
Yes, but the point is, So what is, I mean, so this is how I am describing the whole algorithm on any possible input. Okay, so this is how an algorithm works on any possible input, right? So on given a particular array A, okay, so it will first ask this question: is AI1 less than AJ1? If yes, it goes to. If I answer yes, then it goes to a subtree. And this is the next question it asks. Okay, so yeah, right, but that's a good point. Okay, so the execution of the algorithm is a path from the root to the leaf. Okay, so that's the thing that you've heard in the labs. And yeah, so maybe that is the better way to state this, that the algorithm captures all possible arrays. This tree captures all possible executions of that. Okay, and the maximum number of comparisons is basically the depth of the tree. Yeah.
So essentially this seems like a decision tree.
So you can think of it as a decision tree. Yeah, any algorithm you can think, any deterministic algorithm that works on an array, you can think of it as some kind of a decision tree, right? So it asks these questions, depending on that you get something.
And it gives all possible ways to arrive at a solution.
Right. So yeah, so that's what we're going to say. Okay. So and when we want, so at the end of the day, you've got to come up with some sorted list, right? Depending on your input array, you have to come up with a different sorting order. Alright, so that's this. But the important thing to note that this is a binary tree, because the answer to sorting is binary. We are assuming all elements are distinct. And now, the idea behind the proof is, okay, so suppose I fix some numbers, b1 through bn, okay, and I say that the array A is some permutation of these b's. Okay. Now the main question is, suppose I take two different permutations of the b's. Okay, so suppose we take two different permutations. By 1, by 2 of the b's. Okay. So this is like saying I have two different arrays, both of which, but two different input arrays A. Let me call them A and A prime. They both have the same numbers b's in them, but they are permuted. Okay. So they are two different permutations. The question I want to ask you is, suppose I go back to this tree, and so this is the all possible executions of the algorithm. Okay. So can we say that, is it possible that for A and A prime, you follow the exact same path from root to leaf? So the question is it possible that we take the exact same root to leaf path for A and A prime? Okay, so if it's possible, then what would happen? So you're saying it is possible that, so suppose my tree just consisted of like one node, right? So suppose my tree just did some comparison, and based on yes or no, it outputs some answer. So I want to say that I mean, in this case, it in some sense cannot tell between these two permutations. Okay, so I have two different permutations of these numbers b's, right? And I know that the answers have to be different. Okay, so that the answers, by which I mean the outputs, have to be different. Okay, so the answers should be different. So is this clear? What do I mean by the answers here? The answer is, okay, so what I mean is the answer is essentially a permutation of the given A. Of the input A. Okay. So if I had A and A prime, the right sorted order for these two will be different permutations of the A and A prime, right?
But the sorting will be the same ultimately.
Exactly, but in terms of the A that was given, the order of the A's will actually be different, right? Okay, let's take a very simple example. Okay, so suppose I choose B1, B2, B3, B1, 2, 3. So A could be 2, 1, 3, and A prime could be 3, 1, 2. Then in this case, if I am given this, I've got to output A of 2, A of 1, A of 3. And in this case, in the second case, I've got to output A prime of 2, A prime of 3, and A prime of 1. So in some sense, what I'm outputting is these guys, right? So I've got to say that A of 2 is less than A of 3. Because remember, I don't have actually access to the numbers A's themselves. Okay? This is all a comparisons only model. Okay? So when an algorithm sees the array A, it's only allowed to compare A of 1, A of 2, A of 3. So it will only output something of the kind of A of 2 is the first smallest element, A of 1 is the next, A of 3 is the next after. So in some sense, the answers that it has to output are actually different for these two different permutations of this. Okay. So this is a slightly subtle point. So I'm going to pause here for a bit and see if you guys have questions on how and what I mean by it. Okay, but I think this example should make it clear. Is this, do you have a different explanation?
I'm trying to see why it's 2, 3, 1 is better than 3, 1, 2. So I'm not looking.
Sorry? Oh, this was just an example, right? So A is that, A prime is this. For this example, the algorithm needs to output A of 2, A of 1, and A of 3. Because it doesn't know that, it doesn't know the values. In some sense, it only can compare things. So it's supposed to figure out that A of 2 is the smallest element.
I'll look at the slides.
Yeah. So that's the point. That it's supposed to figure out that A of 2 is the smallest, then A of 1, then A of 3. So you can think of the algorithm as having to output that permutation, the 2, 1, 3, and in this case 2, 3, 1. Right? So that's the idea. Okay. And now the question is, okay, so if we had two different permutations of the original elements A and A prime, like in that example, then is it possible that we take the exact same root to leaf path, still end up with sorted arrays for both?
No,
And why is that?
because the comparisons are different.
So the outputs need to be different, right? So remember, what is a root to leaf path? A root to leaf path is essentially, it asks some query, it gets some hint from about the array. Okay, so it gets some partial idea about what the array looks like. Okay, then goes to the next thing, it asks a different question, gets a different answer. Okay. So if so far all the answers you've got are exactly the same, okay, then an algorithm has no idea whether it was this permutation or the other, right? And the point is that if it cannot tell between these two, A and A prime, just using the comparisons it has done, it's not going to produce different outputs, okay, because this is a deterministic algorithm. Okay. So in some sense, what we are saying is that essentially, so no two permutations of the B's lead to the same leaf node. Because we are assuming that at the leaf node computation ends and it outputs some array. So it outputs the sorted array, right? So somewhere it should be able to distinguish between these arrays A and A prime. Otherwise it's not going to output different answers. And that's the point essentially, that for any two permutations A and A prime of the base, you are supposed to end up at different leaf nodes. Now what does this tell you about the tree? Right? So you have a binary tree in which you know that the number of leaf nodes is at least n factorial. Because there are n factorial different permutations, and no two permutations can end up at the same leaf node. Okay. So in some sense, this is a binary tree with at least n factorial leaves. Okay. It need not be balanced or anything, right? So it's, I mean, for all you know, the tree could look like this. Okay. So this is a 6-node tree, and yeah, so you have 4 here and 2 there, right? So, but it doesn't matter. But we know that there are at least n factorial different leaf nodes. And now what you can show is that if you have any tree with at least some n factor, I mean, if you have a tree of depth k. Okay, so this is another easy lemma. A tree of depth k has at most 2 to the k leaves. So this is actually a very easy theorem, right? So it basically says if you have depth k, then the best possible outcome is you have a complete binary tree, in which case you have 2 to the k leaves. So the fact that some of these things were not leaves can only in some sense help you. Because depth is measured as the longest route to leaf path, not the average or anything like that. So this is a very simple lemma. Okay, and so this is what we have shown, right? So we have shown that you have a tree and it has depth k. Let's say then if 2 to the k were less than n factorial, then you get there's some contradiction, like we said. So it must be that 2 to the k is at least n factorial. Because we've argued that this tree has at least n factorial leaves.
At most.
No, we said we have at least n factorial because we said that no two permutations could end up at the same leaf.
So at most, should it be at most?
I mean, it could have multiple leaves for the same permutation. I mean, for the same permutation, I mean, there's no reason why it could happen, but potentially your tree could be like, I mean, it could ask you some question, your algorithm could ask you some question, then realized, oh, you know, I went along the wrong path, and it could come back and realize that it was this permutation. Okay, so, but that doesn't matter.
So it's exactly a factor if all my numbers are different.
So right, if your algorithm is smart, it will be exactly n factorial. Okay, if it doesn't do any unnecessary paths and stuff like this. Like for all you know, there could be an algorithm that says, hey, let's compare A1, A2. Okay, in the 3 example case, right? It could say, let's compare A1, A2. If it is yes, I go to something, I compare A2, A3. If it's no, I compare something else. And otherwise, and later I could do the same comparisons. I could have basically multiple leaves for the same permutation. Okay, so you do some redundant computations, right? So it is possible, but that doesn't matter. So these kind of redundant computations only save us. We want to prove a lower bound, right? So we want to show the number of comparisons at least so much. If the algorithm was inefficient, then it's even worse. So. Alright, so that's the point. So that's why you know that there are at least n factorial leaves. Okay, because, and for that you need this argument that if you had 2 different permutations, they could not have ended up the same. So that's it then. So then you have 2 to the k is bigger than n factorial, and this is something hopefully all of you have internalized by now. So what is log of n factorial? So which means that okay, k is bigger than or equal to log of n factorial.
2 log n.
What is log of n factorial?
2 log n.
Less than log n log n.
The exponent of this is n squared.
This is less than n log n. N factorial is less than n to the n.
But we want bigger than or equal to.
Oh, sorry.
It is true that n factorial is less than n to the n, and therefore log of n factorial less than n log n. But we want a bigger than or equal to. Yeah. So this is something I remember writing it in one of the notes or somewhere. But it is this is what is called Stirling approximation to the factorial. It's called. Okay, so it turns out n factorial is asymptotically something kind of like n to the n. Okay, so it's actually n by e to the n, roughly speaking. Okay, so up to some 1 by n. Okay, so this is what is called the Stirling approximation. There's some pi's and stuff involved, but up to constants, this is what it is. And what this means is that if I take the log of this is roughly n log n minus n. Again, here there are some constants before the n, maybe there's 2n or something. So, but asymptotically it's at least n log n. Okay, and that's the point. Alright, so any questions on this? So this shows that if you have any algorithm that just works by sorting, then it must take, so nobody has questioned me on this, but I should have written omega out here. Okay, so it needs at least something like n log n steps. Alright, so this is just one example of, I mean, this is not a very, this is not something you should really internalize, but the point I want to make is that sometimes if we restrict the model of computation, like you're only allowed to do comparisons and things like this, then you can actually prove, these are what I call unconditional lower bounds, right? Because you have actually not made any assumptions, you have proved a lower bound from scratch. Okay, so you have said that any algorithm that works like this has to take at least so many steps. The reason I do this example is because not many unconditional lower bounds are known. It is one of the few ones. Okay, so let's now look at a more at a nicer problem. Okay, so this is sorting. This is kind of a toy problem, right? So let's look at a harder problem. Okay, and this is George Boole. So, how many of you have heard of Boolean formulas before? Decent chunk. Okay, so, alright, so Yeah, so this is, if you've taken any like basic logic course or something like this, then you would have seen things like this, right? So in logic you have variables that denote true or false. Okay, so you could have you have variables xi that can be true or false, and you can say xi or xj is basically like saying xi is true or xj is true. One of them at least is true. Okay, so this is false only if both of them are false. Okay. And you have and not also. So xi and xj, and you have things like not xi. Okay, not is just the negation of true is false. Okay, so hopefully all of you can manipulate Boolean expressions, and this is something we implicitly use a lot in computer science. Okay, so I'm not going to go too much into this. But the point is, what is a Boolean formula? A formula is basically, I will denote it by phi. It is an expression that involves these xi's, okay, and it involves some Boolean operations and or and not. So for instance, it could look complicated, so it could be like x1 or x2 and x3 or x4 bar. x4 bar is like not x4, okay, so this can sometimes be written as bar. This is just to save space, or not x4 looks better. So this is just that, and x1 or x3, and I could have the whole thing or x2 bar. Okay. So you could have, this is an example of a Boolean formula. Okay, so it's it's eventually this whole thing. Just like any algebraic expression, but your variables are these, and you have your operators are or, and not. Okay, so that's why it's called a Boolean algebra. Okay, so it's some kind of an algebraic defined on this true false variables. Okay, so any question on what a Boolean formula is? Should be completely clear. Okay, so yeah, so now we say that a formula is satisfiable. Okay. There exists some x1 through xn that actually make it true. So let's take an example. So suppose I tell you x1 or x2 bar. Is this satisfiable?
Yeah.
Sure. And what are some x's that make it true? Yeah, 1, 0, or yeah. So 1, 1 is also fine because it's an OR. So only one of them needs to be true. Yeah, so there's a lot of assignments for this, right? So there's 3 different ones. Okay, so and you could have more complicated ones as well. Now, so the question is, suppose I gave you a formula, can you tell if it is satisfiable or not? Okay, so that is what is called the satisfiability problem. Okay, so if I give you a formula in n variables, okay, so I give you some phi, then ask you, okay, is it satisfiable? Okay. So this, I copy pasted it from somewhere, then I realized this is actually a particularly easy formula. But so you can actually easily tell if this is satisfiable or not. But point is, you could have a very complicated looking formula, and now you're at a loss, right? So suppose someone asks you, is this satisfiable? You got to think about it hard. You got to see, oh, suppose I plug in x1 equals something, x2 equals something else. Is this, is there actually a solution, right, that makes the whole thing satisfiable? Okay. So that is what is called the Boolean satisfiability problem. And it looks like something that just is, it's a question in logic, right? But it's actually a very fundamental question in CS. Okay, so, and the question here is, does there exist an algorithm for this problem, which I call SAT? Okay, so just to, Boolean satisfiability is too long, right? So I will call it SAT. is there an algorithm for SAT that runs in time polynomial in n? So n is the number of clauses, number of variables. Okay. And yeah, so this is a very fundamental question, and this is also called the P versus NP question. Okay, so we'll see a different phrasing of it in a bit, but this is equivalent to what's called the P versus NP question. So how many of you have not heard of P versus NP? Glad everybody has heard of it. So, all right, and why is it so significant? Right, so I mean, I'm calling it the fundamental question of CS, right? So why is it that significant? Well, in some sense, we are asking, so the most natural algorithm you can think of for satisfiability is exhaustive search, right? I mean, you say, okay, I want to know if there are some true-false values that make the whole formula true. So one way to do it is, okay, let's try all possible assignments, and maybe I will find one. So, but this takes time to do the end. So we are saying, okay, can you avoid exhaustive search over this whole thing? But this is still not clear, right? So why is avoiding exhaustive search such a fundamental question? So anybody know the answer to this? Alright, so let me give you some philosophy, okay? So it's like, so let's take any mathematical statement, okay? So suppose I give you a theorem and ask you to prove it, okay? So here I have this example of Fermat's last theorem for one of its easy cases, okay? But it's still non-trivial enough, okay? So suppose I tell you, prove that some equation has no integer solution, okay? And so what does any proof look like? Right? So you have to say, okay, I have some axioms, and from the axioms I deduce something, and from these things I deduce the next step, and so on. Right? So any proof, okay, so suppose I give you a mathematical proof, okay, so which looks like this, and I ask you to verify that it's correct. So hopefully all of you can in principle do this, right? Like if a proof is very complicated, it might take you a while, but it's only going to take you polynomial time, right? In the sense that what you guys will do is, okay, you'll see what is the first step, okay, so yeah, check if step 1 follows from axioms. And in principle, if I wrote down the proof well, then I should be able to say, okay, check if step 2 follows from this and the axioms, and so on. If I wrote a proof in some linear way. And any mathematical proof hopefully will not have cycles, so you can write it in a linear way, right? So this is how you would check a proof. And now suppose I ask you, okay, so what is step 1? Right? If I think of what exactly is step 1, it is some statement. Okay, so it is some mathematical statement. Any mathematical statement, I could think of encoding it as some kind of I could say, okay, does this statement. Okay, so what am I getting at? I want to say that I could think of this as satisfiability of a Boolean formula. Okay? Because step 1 is some expression, okay, so which holds, and I'm essentially checking if step 1 follows from the axiom. So if I had some way of encoding the axioms, okay, so I have encoding of the step 1, encoding of step 1, and I have encoding of axioms. And so on. Okay, then I'm essentially saying and I have some deducibility rules, right? So I say that, okay, this and this implies this and so on. Then essentially I am asking, does step 1 follow from this, which is like saying, does one of the deducibility rules allow me to go from axioms to step 1? And you could think of it as being captured by a Boolean formula. Okay. So I'm not going to go into the extreme detail of it because it's kind of messy, but you can kind of convince yourself that if you had a program that could read a proof and verify if it's correct, then in some sense you could capture what this program is doing by some kind of a Boolean formula, right? Because a program will have certain states. Okay, those states you can think of as being binary. Those are like 0, 1 variables. And essentially the proof itself are the variables that you want to find. Okay, so if you want I can send you some details of this, but I don't want to get into too much detail because it's kind of, it's kind of messy if you go into the details and then you lose the intuition. Okay, so, but the point is that basically any verification process you can think of as some kind of a Boolean formula. Okay. So you can say that if I have any computation that's going on and it's going to output yes or no, you can encode that whole computation by some kind of a Boolean formula. Okay. And now checking whether there are some variables that make it true or false is essentially like finding the proof. So this again you can convince yourself after you think about it for a bit. So I'm just trying to motivate this, so I'm not trying to be very formal here. Okay? But so the point is that any verification can be thought of as computing some Boolean formula and some variables, as evaluating Boolean formula in some variables. Okay, so you can think of, I have a bunch of ands, and this could be like saying, oh, does step 1 follow from axioms? This could be like, does step 2 follow from step 1 and the axiom? Things like that. And I want the and of all of these to be true. So this is the idea. Okay, so you can think of any verification as this, and somehow the variables are what the proof should be. So in this sense, being able to solve satisfiability is like saying, suppose I tell you that the length, find me a proof of length n, then can you actually find me the proof in polynomial time? Okay, so that's essentially what P versus NP captures. Okay, so it's like saying, suppose that I can, so this is another way of saying, so suppose I have a checking time or a verification time. Okay, so in some sense, is solving roughly polynomial verification. Okay, so that's like asking, is there a polynomial time algorithm for SAT? Okay, because verifying whether the formula is true takes time, which is just polynomial. It takes time, which is linear in input. And so what we are asking is solving essentially polynomial in the amount of time it takes to check whether the solution is correct or not. And in this sense, it kind of, so that's why it's a very important question, okay, that it can actually, it's like, many people paraphrase this as saying, can the creative process somehow be made efficient? Okay, not automated, but it's like, can be made efficient. Because you can think, it's like saying, suppose I give you a theorem and I tell you there's a proof of this theorem that involves n different symbols. Okay, and now it's like using this satisfiability algorithm to actually find the proof. Okay, so because when you write out the proof in some language and it has n symbols, and you can verify if it's correct or not in polynomial time. And any verification is a SAT formula. So that's why if you can solve SAT, then you can essentially verify this. Okay, then you can come up with the proof. Okay, so let's not go into this, but the bottom line is that the satisfiability is an extremely important problem, and in some sense it captures this notion of if I can efficiently check something, check whether a solution is correct or not, can I actually come up with the solution in roughly the same time? Okay, so let me write that down because there's a lot of rambling I did, so maybe I should write down just the bottom line of this. Is that we can verify the solution in a certain time. Time t. Then can we come up with the solution? In time poly of t. So this is an alternate way to phrase the P versus NP. It turns out to be equivalent to essentially satisfiability. And the reason I had to hand wave so much is that this is actually proving this formally is a non-trivial theorem. This is what is called the Cook-Levin theorem. It's it's by two of the very famous complexity theorists. This is in the 60s. Maybe it was even just 60. Okay, so this is called the Cook-Levin theorem, and this can be proved formally. Okay, so that somehow this informal statement is equivalent to Boolean satisfiability being solvable in polynomial. Okay, so let me so hopefully you guys are convinced that somehow this captures Boolean satisfiability captures something which is pretty non-trivial. Alright, so this is this. So now we want to, this is all well and good, right? So Boolean satisfiability is one particular problem. Okay, so why is it so significant for us, right? Like maybe we are trying to just solve spanning trees, right? So why do we care about Boolean satisfiability? Okay, so any thoughts? Yeah.
Before beginning to solve it, we must know that we can solve it in polynomial time.
Yeah. Okay. And so that's fine, right? So suppose you are given some different problem. Let's say you're given independent set or something. Then sure, we must first know whether it can be done in polynomial time or not.
Yeah.
But what does it have to do with satisfiability? Yeah.
A ton of other problems can be reduced to satisfiability in polynomial time.
Okay, so this is what we're going to try to see. Okay, so basically we're going to look at the first step in answering the question that he asked, like can we solve this problem efficiently? It turns out answering that question directly is very difficult. Typically. Okay, so you can't all, suppose I give you some problem and say, this is the difficulty we saw, right? Even for sorting, it took us like 45 minutes to prove that you can't do it in better than n log n. And that too under some limited computation model. Okay, so what hope do we have if I told you solve max flow better than, can max flow be solved in linear time? Okay, so then, it's hard to show these things, right? So we want to say that in some sense these problems are related, and this is what complexity theory is all about. So you try to argue that if I can solve this problem better than such and such, then I can solve this other problem better than such and such. And in this sense, satisfiability also plays a fundamental role because it's one of these problems that you can try to reduce to your problem of interest. So before going there, let's see one difference between what we've been looking at and what is, so far we've mostly been looking at optimization problems, right? We've been looking at what to find the max flow or find the minimum cut or find the min spanning tree, things like this, right? So there have always been optimization problems, while satisfiability was just a yes/no problem. You're given a formula and you want to know if there are some x's that make it satisfiability or not. That make it true or not. And but you can easily see there's an easy way to go between these two. And the answer is by saying, okay, you can ask, does a graph have a spanning tree of cost less than or equal to k? And then it's essentially, you can now try to do a binary search for k or something like this, and you can find what is the best value of k. So in some sense, that's why whenever we think of hardness, we think of decision problems. Okay, so this is it's an important distinction. So how many of you have not seen the notion of a decision problem? Okay, so all of you have seen something or the other, I guess. But yeah, this is something to keep in mind. Okay, so usually when we think of complexity of problems, we think of yes/no problem. Okay? And they are not that different from optimization, because most optimization problems you can reduce to yes/no by asking questions like this. You can say, alright, so these are the kind of problems that we want to look at. And the kind of questions we want to ask are can I solve this yes/no problem in a certain amount of time and so on. Okay. So yeah, actually before we go there, so I want to go to this definition of what P and NP are, because that's something that all of you should know. I've phrased the P versus NP problem as a question of, does satisfiability have efficient algorithm? Right? But what are these P and NP? So anybody want to define? Maybe somebody else? How many of you have seen these more than 2-3 years ago? Okay, so plenty of you. So it's you'll take a while to recap, right? So let's slowly recap this. So this is easy. What is P?
Problems solvable in polynomial time.
So these are all problems. So remember, we always think of decision problems at this point. Okay, these are all problems that have yes/no answers. All problems solvable in time, which is poly in input size. Okay. So writing down the instance of the problem takes a certain size, and you want the solution to be polynomial in that. Remember, this is where we had some issues with max flow, right? So the first algorithm was not polynomial in input size. Okay, so this is where it's important. So what is NP now?
Problem solvable in non-deterministic polynomial time.
Yeah, I always wait to hear if somebody says problems that are not solvable in polynomial. So, but that's not true. Okay, so NP is actually a positive definition. Okay, so it's it is all problems solvable in what is called non-deterministic polynomial time. Okay, so this is also a notion of efficiency. Okay, so it says that these are all problems for which there is what is called a non-deterministic algorithm that runs in polynomial time. So first one is so that we understand. So I'm yet to tell you what non-deterministic polynomial time is, but we'll see that in a bit. Okay, but before that, it's important to note that both P and NP are classes or sets of problems, and this is something that you should. Takes a while getting used to. So it's like each problem is, you can think of it as something where it takes an input and outputs yes or no, and we're talking about classes of problems. Okay, so NP contains a whole bunch of problems, P contains a whole bunch of problems, and so on. Okay, so alright, so that's that. So now what is What are non-deterministic? What is non-deterministic polynomial time? Okay, so the ND is that. So what is non-determinism in algorithm? How many of you have seen this definition before but not quite? Okay. So do you want to take a shot at defining this?
I'm not completely sure, but yeah, it has something to do with the concept of the Turing machine.
Okay.
So Turing machine has a tape and computation is like moving across the tape. And there's a variant of a Turing machine which is non-deterministic. And I think it has something to do with whether on a non-deterministic Turing machine you can get a polynomial.
Yeah, so that's one way to say it. Yeah.
Non-deterministic machine can essentially clone itself or reaches a decision point and consider both paths at once. There's a traverse the decision tree that goes by depth rather than forward. Or it can pick the optimal path.
Yeah, so most algorithms, right? So that's a good way of capturing it, right? So most algorithms, what they do is you ask certain questions and then you make a decision and you ask a different question or something like this. This is kind of what we've seen before, right? So, and there's multiple paths you could take. If you think of satisfiability, right? So if I think of trying to find an optimal assignment x1, x2 to xn such that some formula phi becomes satisfiable. Now you could say I try x1 equals something and x2 equals something else, x2 equals 1, x1 equals 1, x1 equals 0, and so on. And in some sense you've got to explore this tree and in the end you know if the formula is satisfiable or not. So it's like you make some decisions and if you are right then maybe you make progress. And in the end, maybe you determine whether the formula is satisfiable. But if you are wrong, maybe you enter no. But ordinarily in an algorithm, if you enter a wrong state, then it means that okay, maybe I've made a mistake, so I have to go back and check everything else. But when you think of a non-deterministic machine, what you should think of is a machine that can simultaneously explore these kind of paths. So actually this, the textbook really does a fantastic thing. It has this Yogi Berra quote that says, if you reach a fork in the road, take it. Right? So that's exactly captures what non-determinism is. Right? In some sense, if you reach a decision point, you just take it. Right? So you explore both sides. Okay, so that's what a non-deterministic machine can do. Okay, so and then at the end, you either accept or you reject. Okay, so what you can think of is non-deterministic polynomial time is you have a whole bunch of decisions. At the end, you are in some state which is either accept or reject. Okay. And a non-deterministic algorithm can essentially figure out if there is, this is a potentially exponentially sized set. And it can determine if there is one yes in that or not. Okay, so it can determine if there exists some yes in this or not. Okay, so if so, you are supposed to tell if that the formula is satisfiable, right? In other words, if all of these are no, it's supposed to tell that the answer is no. So this is precisely what a non-deterministic machine can do. So this again, this is more for out of interest. So yeah, so I would say read up the textbook chapter on this. It does a really brilliant job of explaining this. Okay, so actually these hardness chapters are one of the reasons I got sold on using this textbook, because it really does a really good job. Okay, so yeah, so in some sense you can think of all these choices that you've got to make, and you end up with some situation where you either have to accept or not. And such a algorithm can essentially see if, if there exists at least one yes or no. And that's what a non-deterministic algorithm is. Okay, but again, this is more out of, it's more for people who are curious about this. Okay, and so NP is this class of problems where you can, there exists such a machine. And you can also think of this as the class of problems where you can verify the answer correctly. So what is the answer? The answer is this path that you've got to take. Okay, so in some sense that's what it is. So NP is class of problems with a polynomial sized witness. Okay, so that's the formal word people use for it. And witness you should think of as, so if I had all these choices to make and I want to know if there exists a correct choice that will lead to acceptance, okay, then the witness essentially tells you the choice that you need to make at every step. Okay, so it tells you the path. And there's just a bunch of 0 1s. So that's the path that you need to take to get to some accepting state. So this is another way to write NP. Okay, so we'll not go into this. And SAT is the canonical problem in NP because for SAT the witness is the assignment. Okay. So SAT is the canonical problem. Okay, and so in some sense the question of, so this is why it's called the P versus NP problem, and the question, and we don't know if SAT is in P, right? So we don't know if NP itself is contained in P or not. Okay. So it's an embarrassing question. You would expect that clearly NP is not in P, right? And but we don't know how to prove this statement. And it's extremely difficult to prove even much weaker statements than this. So, yeah, so it's the big open question. But we believe P is not NP. Okay, and why do we now care? So this is where we'll get to what he was saying, that, so what if SAT is not in P? If this satisfiability problem, suppose it does not have polynomial time algorithms, then we're going to see that many other problems are not in P either. And this is what we will look at maybe next class. So essentially what we want to look at is what I call reductions. Okay, and the statements we want to prove are, if SAT cannot be solved efficiently, then neither can my problem X. So suppose you are interested in solving some problem and suppose you can't find a good algorithm for it. One way to do it is to give up and say, okay, let me try some heuristic, maybe it works for some instances, maybe it doesn't. But typically you would want to know, am I missing something, right? And one way to answer this is by saying, okay, no, if I can solve this problem efficiently, then I can also solve SAT efficiently. Okay? And SAT is a problem I don't believe can be solved efficiently, right? Because it's like this, it has this whole philosophy of, oh, can I automate creativity, things like this, right? So SAT I don't believe can be solved efficiently. Now, and the question is, so that's why you would want to prove that it's not, so I think the book of Gary Johnson has a nice cartoon. So it's like, suppose you have to tell your boss that this is a hard problem, right? So you just say, you're not going to say, I can't solve it. You're going to say, hey, I've reduced my problem to SAT, and here are all these famous people, they couldn't solve it either. Okay, so that's one way of capturing all these reductions. Okay, so so this is why we study reduction, because if you have a problem, you want to understand if it's harder than SAT, right? Alright, so what is a reduction? Okay, so let me just formally state what a reduction is, then we can move on. Then next time we'll see some examples. So, let's skip this. So we want to say that some problem B is at least as hard or it's harder than problem A. Okay. So how would you prove such a statement? I mean, this is by this I mean, yeah. Actually, how would you formalize this?
Pretend you have an oracle that lets you solve problem B in some time and then use that to solve problem A.
Okay, so this is one very natural way to formalize this, right? So suppose I tell you, so I have an algorithm which somebody came up with, right? So I have some algorithm which I call or something, and this guy can solve problem B. Then, now I want to say that if I have access to this oracle, okay, suppose I can query this algorithm. Okay. By that I mean I construct an instance of problem B and I get a solution to this. And can I use this to solve problem A? Okay. So can we use this? Let's call this algorithm M. Okay. Can I use M to solve problem A? So this is not as alien as you would think, right? Because you've already seen this in the homework. Like for instance, I told you if you have this problem on a DAG that you can solve, then you can solve some coin change problem using that. Okay. So this is something that we do naturally in some sense, right? Because we have two problems. You might think, oh, okay, so this problem actually captures that problem as well. So in some sense, it is easier than, I mean, it's harder than that problem. Okay, so this is what we want to show formally. Okay, but there's a little bit of tact involved in this. Okay, so how do you formalize this? So one way to say is, I have an algorithm that for A that makes calls to M. Makes function calls to M. Okay, so this is one thing you could say, you could think of. Okay, and these are what are called Turing reductions. So this is one way to reduce. We call this reducing problem A to problem B. And if I can reduce the problem A to problem B, then it means that B is harder than A. Yeah, at least as hard. Problem. Okay. But what we will usually think of are actually something stronger. So these are what are called card reductions. So next class I might mention briefly how these two are different. Okay, but it's a very subtle point. Difference between these two. So and that's important. Okay. And what this says is it's a special kind of a reduction. And what it says is if I want to show that problem A is reduced to problem B, what I want to take is an instance of A, okay, and come up with one instance of B. Okay. And now I use the oracle M to solve IB, and I return the exact same answer that the oracle returned. Okay. So it's similar to this setting here, but it's just that I return M of IB. Do you guys see how these two are different? So is this notion clear? So I want to say that I want to solve instance IA of problem A. I come up with an instance IB of problem B. Okay, so this is, and this reduction has to be of polynomial size. So IB's size has to be polynomial in size of IA. And I want to return M of IB, where M is this oracle that I was showing before. So there's a slight difference between these two notions. So the point is that in the earlier reduction, you had m as an oracle and you could keep making function calls to this. And it's also not necessary that you actually literally output the answer that m returned. Okay, for instance, like this intuitively makes sense, right? So suppose I have a problem called unsat, which is I give you a formula and I ask you, is it not satisfiable? And it's basically the complement of sat, right? Because sat is it satisfiable? And intuitively you would think these problems are equally difficult. Because if I can tell that the problem is not satisfiable, then I obviously can tell that whether it's satisfiable or not. Right? So intuitively these problems are equivalent, right? But turns out in this notion of a reduction, we don't know if there is a reduction like this from sat to unsat. Okay, so that's another big open problem. It's called the NP versus co-NP problem. Okay, so in that sense, these two reductions are quite different. So here, you assume you actually have an oracle to one problem. You can make repeated calls to that oracle, and you can tell if this can be solved. And here, you just have an instance-wise transformation. Okay, and these are what are called car productions. So you transform one instance of this to another instance of P. Okay, and you return the exact same answer. So the reason this is not just a notational thing, there's a deeper significance to it. That's why I want to make this point, that these are two different notions. So, alright, so next time we'll see what this is and so on. Okay? Alright, so let's stop here.